Hi class, here we are ready to start the unit on gases. In this video we're going to look at kinetic molecular theory and how it applies to particles in the gas phase. We are familiar with the idea that all molecules are in constant motion. So everything is constantly moving, whether it's a solid, liquid, or gas. And we know that temperature is proportional to the kinetic energy of those particles. And it's actually the average kinetic energy. So there is a distribution of speeds that we'll discuss in a moment, just like there's a distribution of attentiveness in a classroom. So you might have a number of students with a low kinetic energy who are just, pretty tired, they might be falling asleep. You have students at the other end who are really enthused and excited about the content that's being discussed that day, so they have a high amount of kinetic energy. But then you have a lot of people that are kind of right in the middle where they have an average amount of kinetic energy. And that average kinetic energy is what is proportional to the temperature. Beyond those two postulates, there are some assumptions that are made about particles with respect to gases. One is that the particles move in straight lines and that their direction is random. The second is that the particles are very small, at least relative to the size of the container. So essentially, the gas particles take up a negligible amount of space in that volume. And we also assume that the molecules do not attract or repel one another, so there are no intermolecular forces present between gas molecules. And the last assumption that's made here is that molecules experience elastic collisions. Those are going to be collisions that are similar to billiard balls colliding, where they simply bounce off one another. There's no kind of stickiness that happens there. Okay? And that has to do with the fact that there's no intermolecular forces, so when they collide, they're moving fast enough that they simply bounce off one another, continuing to move in their straight lines in random directions. So those 5 postulates of kinetic molecular theory we will connect back to in various aspects of the gas unit. Let's look more closely at the relationship between temperature and average kinetic energy. So epsilon is what we'll use here to represent average kinetic energy, and we know that kinetic energy is equal to 1/2 times the mass times the velocity squared. So we have mass, and then we will use the root mean squared speed to describe the velocity of moving particles in the gas phase, and that's represented by the Greek letter mu. So mass and root mean squared speed. Let's look at the mathematical equation for root mean squared speed and see what it depends on. So the root mean squared speed is equal to the square root of 3 times r, which is a constant, times the temperature, divided by the molar mass, and the molar mass here is in kilograms per mole. Okay, and that's a little bit tricky, I know, and we will not be doing calculations with this formula, so you don't need to remember the units and whatnot and how this works out, but I think it is useful to see mathematically the relationship between temperature and mass and the speed of those particles. So as the temperature increases, the root mean squared speed would increase. And that should make sense because we are talking about increasing the temperature, which is going to increase the kinetic energy, which means faster moving particles. As the molar mass increases, the root mean squared speed should decrease. So as in the denominator, this number is going to get large, and the whole term is going to get smaller. And that may make sense too. Heavier molecules are going to be moving slower. We talked about the temperature being proportional to the average kinetic energy. So if we have a large collection of molecules, we're going to have a lot of different speeds going on. So we can make a plot of the root mean squared speed on the x-axis and the y-axis with percent of molecules going at each speed. And with a large enough collection of molecules, you'll get what's called a Maxwell-Boltzmann distribution of speeds. And the curve will look much like this. Let's look at what this plot tells us. So we can look at the x-axis. At low x values, we have molecules moving at slow speeds. And we can see that there's some small fraction of molecules that move at slow speeds. as we increase my speed, we get more and more molecules moving at those speeds until we approach a maximum. And this maximum is the most probable speed. So if we had a collection of molecules and you reached in and you grabbed one out, that's most likely speed that that particle is traveling at. As we continue increasing the x values, we get less and less fraction of molecules, but they are moving faster. The Boltzmann distribution shown here tends to shift towards faster moving particles. So we have more faster moving molecules than slower moving molecules. And that will be reflected in the root mean squared speed. The root mean squared speed will not be at the peak of that curve, it will be slightly offset to the right, reflecting the fact that there are more faster moving particles than slower moving particles in the system. Since root mean squared speed is dependent on the mass and the temperature, we can separate those two variables and see how the plots differ when mass is held constant and when temperature is held constant. In the first case, let's look at some curves where we have a constant mass, so these curves represent the same molecules, but we have different temperatures. So we have the pink, green, and blue curves representing different temperatures for the same molecules. Now, can you predict which curve, A, B, or C, corresponds to the particles with the highest temperature? If you chose curve C, you'd be correct, and that's because the curve C has the largest fraction of molecules moving at faster speeds. Because temperature is proportional to the speed of the molecules and average kinetic energy, the faster moving particles are going to have more kinetic energy and will be at a higher temperature. The RMS speed is marked on the curve, and as you can see, with increasing temperature, we have increasing RMS speed for those gas particles. Now in this plot, these four curves represent four different molecules at the same temperature. So we have a constant temperature here and different masses because we're dealing with different compounds. So could you predict in this plot which curve, A, B, C, or D, corresponds to the particles with the highest molecular mass? Recall the relationship between mass and speed. The heavier the molecules, the slower the speeds. So curve A here must represent the molecules with the heaviest mass because they are moving the slowest. They have the lowest RMS speed. Please keep in mind the relationships between temperature and kinetic energy. As temperature increases, kinetic energy increases. And connecting that to something that can be measured, which is RMS speed, we can see that the temperature causes faster moving molecules. And not only that, but molar mass affects the speed as well. So heavier molecules move more slowly. Okay, so thank you for watching this video, and we'll see you next time.